Our notes 2.8. What we're going to do today is we've been talking about models that have been linear. So looking at models that have been linear. Okay, today we're going to talk about things that are quadratic and things that are exponential. Okay, so quadratic and exponential. I know you've talked about those a little bit in Algebra 2. But we're going to find the equations, we're going to use Desmos. Okay, so it won't be that hard. Okay, so by looking at this is the age, passing yards of 32 quarterbacks, and their age. Okay, so their age and their passing yards. We can kind of see that linear would probably not be the best. It'd be okay, but it wouldn't be the best. Probably more of a quadratic model would fit this better. And we can see that right here, this quadratic model. Okay, kind of fits through the middle of the numbers a little bit more, especially with these numbers here at the end. It brings it down at the end. Okay, so what we're going to do is I'm going to put these, we're going to go to do an example here, and we're going to use Desmos to do it. Okay, so here's a problem. How is the braking distance for a motorcycle related to the speed the motorcycle was doing at the time? So gather some data to answer this question. Speed limit, okay, so how fast were they going in miles per hour, and the distance needed to come to a complete stop when they put the brakes on. Okay, so what we're going to do three things. We're going to calculate the quadratic model. We're going to sketch the scatter plot and come up with a model, and then we're also going to interpret the last observation. So find the residual for this last observation. Remember, residual is the actual, which is this, minus what's predicted. Okay, so I'm going to go to Desmos, and we're going to get that model here. Okay, so I just plotted the data. This is the miles per hour, how fast the motorcycle is going. This is this braking distance it needed. Okay, so if I hit this little thing here, there's our data. Okay, now linear might be an okay model, but you see how it's kind of rounded here at the bottom a little bit. So I think a quadratic model might be a little bit better. Okay, so the quadratic model, okay, you can write this equation down, make sure you have this. Okay, we're going to use y1 tilde a. Okay, start out the same way as linear, but instead of mx plus b, we're going to make it a quadratic. So we're going to say a x1 squared plus b x1 plus c. Okay, so you can see that model. It's probably a little bit better model for how it goes through those points there. Okay, so from this model, we can see that our equation is y is equal to 0.04223x squared plus 0.33x minus 2.29. Okay, so we can write down that model. And this is also our scatter plot that we did there. Part C, we want to calculate the residual. So I'm going to go back to paper for that. Okay, from Desmos, we had come up with this equation. If you want this equation, what we typed in again, we had y1 tilde m x1, sorry, that's the linear one, y1 tilde a x1 squared plus b x1 plus c. That's what you typed into Desmos, and it gave you your a, b, and c for your model here. Okay. So next thing we want to do is we want to come up with the residual for this last point. Okay. Remember, our residual is our actual minus our predicted. Okay. Our actual braking distance for 48 miles per hour was 110.33. Our predicted is what we have to plug this 48 into this equation here. So 0.043 times 48 squared plus 0.33 times 48 minus 2.29. Okay, when I plug it in there, I get around that number right there. Okay, so about 112.62. Okay, so if I subtract those, I get a residual of negative 2.29. Okay, now if you think about what that means, remember we had these points, right? We had this here. It means that this point was a little bit below of what we would predict would have to happen at 48. Okay, so the breaking was 2.29 feet less than predicted. Okay, so there we're talking about the residual. We calculated it and we also interpret it then as well. Okay, so there's one other model we're going to talk about, which is called an exponential model. So a lot of things grow exponentially as well. So you can see here, it comes down like this. If it was going to go back up here, that we could use a quadratic, but it kind of keeps going down here. So this exponential model is our better model here. Okay, so I'm going to do an example here on Desmos. Okay, I'll give you the situation first and then we'll go to Desmos. A random sample of 14 golfers was selected from 147 players on the Ladies Professional Golf Tour. The total number of money won during the years in dollars and the average number of strokes above 70 for each player were recorded. Lower scores are better in golf, by the way. Okay, so here's our data. So here's their score. It's above 70, their average score above 70, and their earnings. Okay, so I'm going to go to Desmos, put these in, and show you how to get an exponential model.
Okay, so I've put the data in here. This is the score from 70. So notice 0.16 is the lowest score, the best golfer. Made over $1.6 million. That person's up here. And you can see the graph makes more of a exponential sort of decay sort of model here. Okay, so to get the equation here, we're going to hit y1, okay. We're going to have a times b raised to the x1. Okay, so that's what you type into your equation there. Notice it gives you your a and your b here. If you think about this number right here is times 10 to the 6 means you move this decimal place over 6 places, and that gives you what your a value is. And you can see our b here as well. Okay, so now that we have that equation, I'm going to go back to paper and talk about the residual for that as well.
Okay, so from Desmos, we typed in y1 tilde a times b to the x, and it gives us this equation right here. Remember that was 1.87 times 10 to the 6th, so we move it 1, 2, 3, 4, 5, 6 places over, and then b to the x power. Okay, so now we want to find a residual for the last golfer on the list, this person right here. Okay, how residual is how much error there was in our guess. Okay, it's our actual minus our predicted. Okay, our actual amount of what she made was $1,626,297. To find what's predicted, I would type in 0.16 in here. I'm just going to use the book's answer here. They rounded a little bit differently than I did, but okay, so when they plugged it in here, they got 1.28 million. Okay, and if I subtract those two, I get positive residual of that much money. Okay, so if you think about this, this person made more, and not quite a lot more, than what was predicted for her based upon that line. Okay, so she made this much more money than what was predicted. Okay, so that would be the interpretation of that. Okay, the last thing we want to talk about is how do you know whether it's going to be linear, quadratic, or exponential? Okay, so what we can do is we can look at these residual plots. Okay, so this is if we did a residual and we looked at all of their okay, so if we did an exponential and we looked at the number of all the residuals, these are all the residuals plotted. Okay, and if you remember, okay, well, let's get back to this. We looked at the relationship between cost of a 30-second commercial during the Super Bowl and the Super Bowl number. The scatter plot at the right clearly shows the relationship is nonlinear. Okay, see this? We know it's nonlinear there. An exponential model and a quadratic model were calculated, and then they shows the residual plots for those. Okay, so an exponential model would come up like and go through like this. Okay, that's the exponential model, whereas the quadratic model would come and go like that idea. Okay, so which one would be more appropriate? Okay, by looking at the residual plots, if you remember, we want to have a good scattering with no patterns. Okay, but notice we have a certain pattern there, don't we? Okay, here we have a pretty good scattering above and below throughout. So the quadratic model would be a better relationship, better model there to use than the exponential. And that's how you can tell between the two.